Hello, in this lecture I'm going to discuss integration and differentiation, providing a brief review in order to remind us of some of the primary techniques involved with these tools that will hopefully get us set up and ready to move forward with our course. The notes that I'll be working through are available using the lectures link in the toolbar in BBLearn. Thinking back on your previous calculus courses, you recall that the two primary techniques that are introduced in those courses are differentiation and integration. Both of those rely on limits, but for the focus of this lecture, I want to discuss differentiation and integration. This is not intended to be a full review of everything that you learned in your previous calculus courses. I just want to look at some examples as a brief refresher. Let's start by looking at differentiation. I trust that you're familiar with taking derivatives of the popular basic functions, polynomials, trig functions, exponential functions, logs, etc. And then hopefully you remember that there are three main rules associated with taking derivatives of functions that are more complicated. First rule is the product rule. Second rule is the quotient rule. And then lastly, the chain rule. This is a typo. I should say chain rule. Indicates how to take the derivative of composite functions. The notation for these varies slightly, so you may have written these in a slightly different way in your previous courses, but the structure of these rules is hopefully familiar. Next, we have a few examples that remind us of how we apply these three rules. In example 1, we're asked to differentiate each of several functions. The first function here is f of x equals e to the x cos of x. I noticed that this function is built out of two functions whose derivatives I know readily, and those two functions have been multiplied. So that indicates that I'm going to be using the product rule. Referring to the notation that was stated previously, I could name one of these f of x and the other g of x. I prefer to just identify those two separate ingredients and apply the product rule as I remember it. The way I think of the product rule is to leave one of the functions alone. Here I'll leave e to the x undifferentiated, and then I'll multiply by the derivative of the second function. In this case, the derivative of cosine is negative sine of x. And then I reverse the roles. Next, I'll leave the second function alone, undifferentiated. That's just cos of x. And here, I have to take the derivative of e to the x. As you recall, the derivative of e to the x is itself. It's just e to the x. So I can write that there. In this particular example, it's relatively easy to take one step of simplification, but just note that in general, we won't be required to simplify derivatives when we calculate them. So there is my final answer. Let me scroll down to the next part. In part B, I clearly have a quotient of two functions, so I'll be applying the quotient rule. Following the required structure, let me go ahead and work through those calculations. Let me explain the ingredients that I've ended up with here. My quotient rule tells me to take the denominator and leave it undifferentiated, and then multiply by the derivative of the numerator. So here I have the derivative of x minus tangent x yields 1 minus secant squared. I then reverse the roles. I use my numerator, undifferentiated, and here I have the derivative of the entire denominator. So in this case, it's simply e to the x. And then I just take my denominator and I square it. Again, I'm not going to take the time to simplify that for the purposes of this example. I'm just trying to demonstrate that differentiation rule, so I'm satisfied with that answer. Let's scroll down to the part C. Here we have a composite function. I have the function t cubed inside of the function arctangent of something. So that composite function indicates that I will be applying the chain rule. To take the derivative of a composite function, I always differentiate the outer function first. So the derivative of arctangent of something is 1 over 1 plus that something. So if I had arctangent of x, the derivative would be 1 over 1 plus x squared, as you hopefully recall. In this case, the inside piece is t cubed, so that's what I'm going to put in here, and then I need to square that. But applying the chain rule, I also have to remember to multiply by the derivative of this inside function. So the derivative of t cubed is simply 3t squared. This one, I could do a quick step of simplification. I'll have 3t squared over 1 plus t to the 6th. And I'll leave that as my final answer. We have one more example, part D. In part D, there's kind of a lot going on. I notice a product and a quotient, and I have an e to the... So we're actually going to be applying several of the rules as we differentiate this y of t function. So first and foremost, I have a quotient. So the first rule I have to apply will be the quotient rule. So let me write out the basic structure of the quotient rule. Here I've just written out the basic structure. So I have the first I have the denominator undifferentiated, and then in the brackets here I've left a space to take the derivative of my numerator. And then I will subtract the numerator undifferentiated, and then in the brackets I've left a little space to take the derivative of my denominator. The derivative of my numerator is going to be a little complicated here because I do have a product. So I need to apply that product rule. When I do, I get t e to the t plus e to the t. And here in the second set of brackets, I'll take the derivative of this denominator. Derivative of 1 is 0. And then when I differentiate e to the negative t, the derivative of an exponential function is always that exponential function itself. But technically I have e to the t inside that exponential function. So I'm technically applying a chain rule. So I'll multiply by the derivative of that inside function, which in this case will just give me negative 1. Once again, I'm not interested in simplifying this. I just want to use this as a demonstration of the different differentiation rules. Let's move on to example 2. In the short paragraph before example 2, I simply say that not only should we be able to evaluate derivatives, but we should know how to use properties of the derivative to infer or deduce information about the original function. Specifically, that those properties typically hinge on whether the function is increasing or decreasing. And as you recall, if the function is increasing, that will be indicated by a first derivative, which is positive. And if the function is decreasing, that will be indicated by a first derivative, which is negative. Usually we go a step further than just identifying increasing and decreasing intervals in order to be able to identify extreme values. These are maximums or minimums. And we typically do so by finding the critical points, etc. We'll demonstrate that process in example 2. Example 2 asks us to find and classify all of the critical points of the function y of t equals t e to the negative t. First thing I need is to find the derivative. Hopefully you agree that I've correctly applied the product rule and the chain rule to calculate that derivative. Now in this case I need to do a few more steps with this derivative, so it will help to do some simplification. Next, in order to find the critical points of my original function, those are the points at which the function potentially changes from increasing to decreasing. In order to find those critical points, I'll set this first derivative equal to 0. Doing so yields the equation 0 equals negative t e to the negative t plus e to the negative t. And I'm going to try to solve this equation for t. You can clearly factor out an e to the negative t. Now I have a product of two quantities which yields 0, which indicates that one of those quantities must be 0. To proceed algebraically, I'll take the two quantities, and set them individually equal to 0, this first equation has no solutions. The function e to the negative t never equals 0. And the second equation is easy enough to solve. It tells me simply that t equals 1. So t equals 1 is the only critical point of this function. So if this function has a local maximum or minimum, it must occur at t equal to 1. You may recall that there are a couple techniques to determine whether this critical point yields a max or a min. One method is to put that critical point on a timeline and then test points on either side by plugging them into the derivative to determine if the derivative is positive or negative on either side of that critical point. Let's use that approach. A possible test point would be, say, t equals 0 on the left. A convenient test point on the right would be, for example, t equals 2. So what I'm going to do is I'm going to plug both of those into my first derivative. So I'm interested in finding y prime of 0 and y prime of 2. I don't technically need to know the actual values. I'm just curious whether this derivative is positive, which would indicate that the function is increasing on this interval, or if this derivative is negative, which would indicate that the function is decreasing. I will go ahead and plug this in, but again, my concern is primarily whether the overall value is positive or negative. Plugging in t equals 0 into this expression for my first derivative yields the number 1, which is positive. Applying the same procedure and plugging in t equals 2 into this first derivative yields a value of negative e to the negative 2, which is a negative value. So filling in those details on my little diagram here, it tells me that to the left of my critical point, my derivative is positive. That means that my function, y in this case, is increasing. Similarly, I can note that to the right of my critical point, first derivative is negative. So that indicates that my original function is decreasing. So now I can picture in my mind a function which is going uphill prior to t equals 1 and then turns and goes downhill after t equals 1. So that indicates that this critical point yields a local maximum value. You may remember from your previous calculus courses that there are further steps that we could take to determine if this is a global maximum, but for the purposes of this review, that's all the detail that I want to put into this example. Moving on to example 3, we see an example of a derivative that we will need to interpret in terms of a rate of change. As the little paragraph there mentions, we're accustomed to using the context of position, velocity, acceleration when it comes to interpreting derivatives, but we can interpret the derivative of any function, not just a position function. So the next couple of examples demonstrate that. In example 3, it says we're going to suppose that the energy exerted by a fish, which is swimming a fixed distance L, is a function of the velocity at which the fish swims. So just to sort of pause and wrap my head around this, I got dependent variable, energy, and that is dependent on velocity. So I imagine a fish is swimming some fixed distance, so this value, this variable L is not going to change. So maybe it's 5 meters, whatever we want to imagine it to be. And then how much energy that little fish exerts is going to be a function of how fast it tries to swim. Makes sense. Next indicates that this relationship can be modeled using the expression E of V equals a v cubed times capital L over v minus u. So an additional variable here, u, and a as well. Those are explaining this next sentence. A is a proportionality constant. We're going to assume that a is a positive constant. And then u is the velocity of the current. So that's measuring how fast the water is moving. We're asked to find the velocity that minimizes the energy exerted, assuming that all other quantities are constant. Before I get started with the calculus side of this problem, let me just note that I can do a little bit of algebra by rewriting this energy function. Value a here is a constant, L is a constant, so when it comes to differentiating, those will remain unchanged by the derivative. So I think it'll be helpful to sort of isolate the variable v in this expression by simply taking this L, moving it over, and then writing the v's in a single fraction. So now, in order to find the velocity value that minimizes energy, I'm going to follow a procedure very similar to what I did in the previous example, by which I will identify the critical points and then try to categorize those critical points in terms of whether they yield a minimum or a maximum. First step in doing that is to calculate the derivative. Again, the AL is constant, so it's unaffected by the derivative. And now I have a quotient. So let me apply the quotient rule to calculate the derivative. I should note that because of the structure of this energy function, we cannot have v equal to u, which would yield our denominator of 0. So that's going to be a detail that we have to keep an eye on throughout the rest of the problem. And then I just wanted to point out that this is the derivative of my denominator, and we are considering u to be constant. So the derivative of v minus a constant would just be the number 1. So my next step will be to set this derivative equal to 0 in order to identify the critical points of the function. And I will set the derivative equal to 0 and do some algebraic simplification sort of simultaneously. Next, I'll note that AL is a constant, and I should be able to divide both sides by AL. So that will sort of cancel from this equation. Similarly, my denominator is non-zero, so I should be able to multiply both sides of the equation by that denominator as well. Although this expression looks rather complicated, once I do those to clean it up a little bit, simplify my numerator, I'm left with a relatively simple expression. I'm now left with a product of two quantities that equal 0. It's a very common thing that we run into. And so in order to identify the values of v that will make this expression true, this equation true, I'll set each of those quantities individually equal to 0. This first equation says v squared equals 0, which implies v equals 0. So the fish is dead, or the fish is not moving. There's no velocity. So it's not a particularly interesting case, so we'll kind of take the liberty of ignoring that. Oops, notice the typo here. This second quantity should have a 3 in it. Setting this expression, or this quantity, equal to 0 does yield an interesting expression that says that v equals 3/2 u. So there is one kind of interesting critical point. And following the same procedure that we did in the previous example, I could verify the values of the derivative, the sign of the derivative on either side of this. I'm not going to do that in this particular example, but just if you want to, you can test v equals 2u or v equals something to the left of u, 3/2 u, and verify that this does yield minimum value. Let's go ahead and take a look at the next example. We're going to suppose that the size of a population p with respect to time is modeled by the following equation. I just stop there even before I look at the equation. That's telling me that the function that I'm interested in is a function p for the population, and that population function is a function with respect to time. But notice that that is not what the equation tells me. Instead of the function being defined explicitly in terms of time, which is what we'd be accustomed to, we're actually told what the derivative of the function is. So if I wanted to, notice this is dp dt, so I could write that as p prime of t. So I'm not given information about the function itself directly, but I'm given information about the derivative. In this particular context, since p is a population, we could maybe think of this derivative as the growth rate of that population. But again, what's interesting is that that growth rate is not defined in terms of time explicitly. The growth rate is actually defined in terms of the population. So the growth of the population is modeled in such a way that how fast the population grows depends on how big the population is. That's kind of an interesting feature that's worth noting. So this is a different type of equation than we're accustomed to dealing with. That's okay. Let's see if what sort of information we can get from it. In part A, we're asked to try to determine when the function is increasing or when the function is decreasing. We of course know that as the fact that we've used in the last couple of examples, increasing means that the derivative of our population function should be positive, and decreasing indicates that the derivative of our population function be negative. Let me just go ahead and note too another little detail. Since we're talking about population, I'm going to go ahead and assume that the population is always positive. So if I'm modeling a rabbit population, I don't have negative 35 rabbits. So can we use this equation, which doesn't give us the function directly? Nevertheless, it gives us information about the derivative. Can we use this equation to determine when that derivative is positive and when that derivative is negative? I'm going to go ahead and rewrite my derivative equation down here. Lowercase k is a positive constant. Capital P is I just said my population is positive. So this first term here, k times p, is always going to be positive. And then the expression that I have in the parentheses is capital P, my population value, over capital K. Capital K is also assumed to be positive. Let me just go ahead and note that this portion here is always positive. So the question comes down to, is this expression 1 minus p over k positive or negative? If this expression is positive, then we'll have a positive times a positive, so my overall derivative will be positive. If instead this expression is negative, we'll have a positive times a negative, so my overall derivative will be negative. I think I can figure that out. Let's see. Let me go ahead and kind of write a conclusion here. P prime of t will be positive if, and then P prime of t will be negative if. So if I just focus on the structure of this quantity here, I have the number 1 minus a fraction. And so this overall expression will be positive if this fraction is less than 1. I'll have 1 minus something smaller than 1. So this overall expression will be positive if this fraction is less than 1. That is, if P over capital K is less than 1. Another way of saying that is that capital P is less than capital K. Applying that same logic can actually determine that the overall derivative will be negative if that fraction is greater than 1. That is to say, if capital P is greater than capital K. The fact that I'm directly comparing my population value with this constant k suggests that k is a value of the population. And in this context, that is a true assumption. So capital K is some particular value of the population. So again, if I'm modeling rabbits, capital K would be some number of rabbits. And this is saying if my population is less than that number, the population will be growing, has a positive growth rate. But if the population is greater than that number, the population will be decreasing. There's actually a third possibility. If P over K is exactly equal to 1, that is to say, if my population is exactly that sort of threshold value K, then my derivative will equal exactly 0. So that means that I'll have no growth. I'll have a perfectly flat population. Let me take a second to kind of draw out a picture of some possible population functions which satisfy these criteria. So far, I've laid out the basic structure of the graph. Again, we're graphing some function p of t, even though at no point in this problem have we explicitly identified what that function is. But we know that if the population equals this threshold value k, the derivative equals 0. So I've got a perfectly flat population function. For population values in this region, the function should be increasing. But notice that it can't increase to the point that it breaks through that threshold. So even though these functions will be increasing, as they approach the p equals k value, they will level off. So I could have potential functions that look something like this. My drawing isn't great, but you get the general idea of what's going on. At the same time, if I ever have a population value that's greater than this threshold, those functions will be decreasing. They have a negative slope. Again, as I approach this threshold value, they won't cross through it, but they'll flatten out. The slopes will approach 0. So I could have potential functions that look like this. So what we've actually got is a whole family of functions that satisfy this relationship. And even though we don't have an explicit expression for any of those functions, we've got a pretty good sense of what this family of functions looks like. For the purposes of this video, I'm going to go ahead and skip part B. I will fill it in the notes, and so you can come back and look at the solution after you've worked through the rest of the lecture. But for right now, I'm going to go ahead and skip part B. Next, I want to turn our attention to integration. On the one hand, integration is just the inverse process of differentiation. That said, I don't know if this is your experience, but in my experience, I feel that trying to enact this process backwards, that is, trying to anti-differentiate, can be much more difficult than enacting it forwards, that is, taking the derivative. And just as an example, in this first paragraph here, I have us consider the function e to the negative x squared. To calculate the derivative of this function, it's a pretty straightforward application of the chain rule. The derivative of an exponential is that same exponential, and then I just need to take the derivative of the inside function, multiplied by that. But as you may recall from your previous calculus courses, to try to find an antiderivative of this function is impossible. So if I was to say y prime equals e to the negative x squared, it's a simple equation. Here I've got some function, I guess I don't know what the function is, I'm just calling it y, but I'm saying that its derivative equals this e to the negative x squared. This equation can't be solved analytically. So I'll just make a little note that this has no solution. So we could spend a lot of time reviewing integration, but I'm just going to kind of hit the highlights. As I mentioned in the next paragraph, of all of the integration techniques that you've learned in your previous courses, the two primary techniques that we will use most frequently are going to be U-Substitution and integration by parts. Some other techniques, specifically partial fraction decomposition, will show up throughout the semester, but those two techniques, substitution and integration by parts, will be the main ones that we use over and over. So let's take a look at a couple of examples to kind of remind ourselves of those techniques. Let's look at example 5. In example 5, we're asked to evaluate several integrals. I'm going to work through some of the steps sort of quickly and just identify some of the key features of these integrals. In part A, I notice that I've got a fraction. I recall that there is no quote-unquote quotient rule for integrals. And so what I have to look for is I have to look at the structure of these components. My denominator is a cubic function, and my numerator is a quadratic function. And I know that there's a special relationship between cubics and quadratics. Specifically, the derivative of a cubic will give me a quadratic. So that suggests that I'm going to try to use the technique of U-substitution. And again, there's different notation for this, but the way that I write out U-substitution is I identify what my U will be. In this case, I'll pick U to be my denominator. Du will be negative 3x squared dx. I don't exactly have negative 3x squared dx in my integrand. I do have x squared dx. And so it's common to accommodate this coefficient by just dividing by it. So I would say negative 1/3 du equals x squared dx. And then I think of U-substitution as identifying pieces in a puzzle and then making sure that those all come together to create my original integrand. So using this substitution, I could rewrite my original integral. I could bring the 6 out front if I felt like it. And then instead of x squared dx, I'm going to make the substitution in 1/3, negative 1/3 du. And then instead of 1 minus x cubed, I will make the substitution and write that denominator as just u. Cleaning that up a little bit, I get negative 2 times the integral of du over u. And then I recognize that 1 over u is, when I integrate that, I get simply natural log of the absolute value of u. Since I have no bounds on my integral, I got to remember to add that c, constant of integration. And then my problem started with x values, so I want to make sure it finishes with x values. So I'm going to undo the substitution, and I'll write my final answer as negative 2 natural log of the absolute value of 1 minus x cubed plus c. It's actually, if you remember rules of logarithms, there's an extra step or two I could do incorporating this coefficient. But I'm going to leave my answer at that. Let's take a look at part B. In part B, I again have a couple functions, a couple sort of components to my integrand. But this time I have e to the negative t and t. And if I try to do a u substitution where I use negative t as u, the pieces don't line up because du will just be dt, and I'll still be left with this t out here. So I have two functions that are unrelated, so that indicates to me that I'm going to use integration by parts. Once again, there's a couple different notations for this. What I'm accustomed to doing is taking my original integrand, breaking it into two pieces. If you remember, I'm going to choose for u something which simplifies when I differentiate it. In this case, given the option between t and e to the negative t is a much better choice. And then the rest of my integrand will be, I then have resulting ingredients based on those choices of u and dv. Notice that this step from dv to v is an antiderivative. And then I've got a certain structure that's going to enable me to move forward with evaluating this integral. I should have noted that I'm actually going to kind of cheat, and from the very beginning, I'm going to pause the endpoints. So as I move through these next couple steps, I'm going to leave off the bounds on this integral, and then we'll make sure to incorporate those before I'm finished with the problem. Structure of integration by parts, I always remember in my little table, I got to take that times that minus the integral of that times that. So that yields, and again, technically, both of these quantities are evaluated from 0 to positive infinity. Simplifying a little bit. And I recall that when I do integration by parts, I'm always left with an integral, but the goal is that this second integral that I'm left with at this point will be simpler than the one that I started with. And that's true in this case. So I can now evaluate this final integral. And now I'll go ahead and reincorporate my endpoints. And as you recall, since one of my endpoints is infinite, I actually need to incorporate an appropriate limit. And so I'm not allowed to plug in infinity. What I'm going to do instead is I'm going to go ahead and deal with this upper bound by introducing an appropriate limit. This second quantity is a constant, and so I can just go ahead and simplify that. In fact, this is 0, this is negative e to the 0, so this is negative 1, so this will be plus 1. But to evaluate this first limit, it's a little bit more complicated. Let me look at this second component. The limit is t grows without bound, e to the negative t. E to the negative t is actually equivalent to 1 over e to the t. And so if I imagine t growing without bound in this expression, I have a constant numerator and a denominator that's growing without bound. I know that that overall fraction will approach 0. So I know that this quantity here goes to 0. This first expression is a little bit more complicated because I technically have t over e to the negative t. Let me rewrite that. Here I've included the 0 that I already reasoned would be the value of this limit. So now as I look at this limit, I technically have a numerator and denominator that are both growing without bound. So if you think way back in your calculus experience, you know that if I have a fraction and I'm taking the limit such that that fraction is approaching a quantity of the structure infinity over infinity, I'm going to need to apply L'Hopital's rule. Hopefully you recall that to apply L'Hopital's rule, I'll differentiate the numerator, differentiate the denominator, and in doing so, I actually end up with a fraction which is similar in structure to the one that we just discussed. So I'm going to skip the details a little bit here, but I'm going to go ahead and conclude that this limiting value, this value will have a limit of 0 as well. That leaves an overall value for this expression of just 1. Kind of a lot going on in that example. Hopefully you understood as I went through it, but please make sure you go through and work through those steps again to understand all of the details of what we just did. Part C is a very interesting problem, but it's a little bit beyond the scope of a standard review. So for the purposes of this video, I'll go ahead and skip that. I will fill in the solution, and so if you look in bblearn later and find the completed version of these notes, you will see a solution to this example, but for the purposes of this video, I'm going to go ahead and skip it. Scrolling down to the bottom of the page, I just have a couple closing remarks. I'll admit that some of the examples that I've chosen in this lecture were pretty challenging, and I did so just to sort of demonstrate some of the things that I think we can be capable of once we're competent with integrals and derivatives. That said, maybe you feel a little bit rusty and you want to check where your skills are at in terms of some more fundamental derivatives and integrals. If so, you can go ahead and jump over to Webwork. Webwork is the online homework system for this course. There's a link provided for Webwork in bblearn. And the very first set is called Set 00. And that set 00, is a review of some basic differentiation and integration problems. If you're not familiar with Webwork, it will provide immediate feedback, whether you've input a correct or incorrect answer. It'll give you an opportunity to continue retrying that problem until you've got it correct. And in the final paragraph, I just want to make a note that if you are having issues with derivatives and integrals, maybe you just feel a little bit rusty, one resource that I would point you towards is the sort of homepage of the author of our textbook. In addition to the textbook for differential equations that our author has written, he's also written textbooks for several other courses. An algebra course, Calculus 1, Calculus 2, and Calculus 3. And for all of his other courses, there are notes which serve effectively as a complete textbook for the course. And then another very valuable resource is practice problems. And so as you're working through set 00 on Webwork, if you feel like you need a little bit of review with, say, derivatives, can go ahead and click on these practice problems. Scroll down, maybe you're struggling with the chain rule. And within the practice problems, if you click on chain rule, you'll see a number of problems that provide, in this case, derivatives, and then full solutions are provided. So you can try calculating the derivative yourself, and then you can take a look at the solution that he has provided, double check that you're correct. So this set of notes is pretty robust. It definitely goes well beyond our differential equations class, and so I would encourage you to utilize this if you need some help reviewing these topics right now at the beginning of the semester or at any point throughout the rest of this semester.